Hello everyone. This video is to do a couple of things. It's to explain the derivation of our four constant acceleration equations, to give you a mnemonic device for remembering them, to talk about how units can be helpful in analyzing problems and avoiding errors, and also to slide that a little bit closer, and also to talk about the formal writing requirements for the next problem set. I'm going to ask you to use all of a number of problem solving elements so that you can intentionally practice sort of structured problem solving. The goal is that even if you don't need all of those structured elements for the problems that you'll be practicing on, those things will be helpful to you on harder problems when you have trouble with those. You can see in my problem solving document and also my writing conventions document a little bit more about the wisdom behind those rules, but this video will explain the rules. All right, with constant acceleration, we said that acceleration is constant and velocity then is linear, and position is quadratic or parabolic. So let's just take a look. That's our graphical model. And so I wrote this blue equation here saying that if we consider a time interval between some time t1 and some time t2, it looks like this object is undergoing some certain displacement. And that displacement shows up as the integral of the velocity time graph during that time interval. And it's that blue shaded area, which is a trapezoid. And so I can use my geometry skills and remember that the formula for an area of a trapezoid is 1/2 times the sum of the bases times the height of the trapezoid. And in this case, the bases are these vertical pieces. Those are the parallel sides. This base on the left has a length of v1, and this base has a length of v2, so the sum of the bases is v1 plus v2. And the height of the trapezoid is delta t. So that's why I say the displacement is v1 plus v2 over 2 times delta t. So this is a true statement about an object undergoing constant acceleration. If it starts with velocity v1 and ends with velocity v2 and takes some time delta t to achieve that change in velocity, then it will have covered a displacement delta x during that time. Here, let's see what I'm doing. I'm drawing the acceleration time graph. And we had said from our lab that the change in the object's velocity during a time interval is equal to the integral of acceleration. It's like this shaded box, this rectangle here. And the change in velocity, the object's change in velocity, is equal to the amount of acceleration that it's experiencing times the delta t, the time interval that we're considering. And so this is a statement of the that the change in velocity is the integral of acceleration, and a delta t is the integral of acceleration when the acceleration is constant. And substituting for the delta, I guess, change is always final minus initial, so v2 minus v1 is a delta t. And I've just algebraically rearranged this to form another equation. Now look what we have here. Delta x equals v1 plus v2 over 2 times delta t. That's a true statement about some variables regarding this object's constant acceleration. And also v2 equals v1 plus a times delta t. That's another true statement about this object undergoing constant acceleration. This is an equation, well, let's count the variables. We've got delta x, v1, v2, delta t, and a. 5 variables in total. This one up here lacks the acceleration. This equation here lacks the displacement, delta x. And you could imagine algebraically combining these to make a new equation that lacks, say, delta t, or a different equation that lacks v2. And in fact, I'm not going to talk all the way through it, but you can see on these slides I do that and get 2 more equations for a total of 4 equations that relate 5 variables having to do with constant acceleration: delta x, v1, delta t, a, and v2. These you need to memorize, and I will show you how to memorize them right now. And it goes like this. Learn to say this with me in this video. 5, 6, 7, go. Delta x equals v1 delta t plus 1 half a times delta t squared. Delta x equals v1 plus v2 over 2 times delta t. v2 equals v1 plus a times delta t. And v2 squared equals v1 squared plus 2 times a times delta x. Yeah. So you need to memorize those, and I wouldn't do that. I wouldn't make a public video with me doing that unless I thought that mnemonic would be helpful to you. Here's how problems go. Problems in the constant acceleration genre generally give you 3 values and ask a 4th. And so you need to pick the one equation that links those 4 variables, the 3 given and the 1 asked for, and then you need to do some algebraic rearrangement of the variables in order to solve for what you want to solve for. Great. So let's do an example. Oh, no, let's not do an example. Let's talk about units, which are your best friend. Could this be a physics equation? v2 squared equals v1 squared plus 2a delta t. Man, it's the quiz, and I'm trying to remember that formula, and I think this is it. Could this be it? If you're on the quiz and you think this might be a real physics formula, I'll give you a way to test whether it might be. Let's look at the units. v2 squared here on the left-hand side of the equation would have units of meters per second quantity squared, or meters squared per second squared. v1 squared would have the same units, and then let's see, 2 doesn't have units. A has units of meters per second squared, and delta t has units of seconds. And so let's see, could the units of this work? On the right-hand side, meters squared per second squared plus meters. You can't add meters squared per second squared plus some number of meters, just like I can't add 3 hippopotamuses plus 2 oranges. It's like adding apples and oranges and hippopotamuses. You can't add them. You can't add them. You can only add quantities that have the same units. That's not true of multiplying and dividing. You can multiply and divide quantities of different units, but you can't add quantities of different units. And so the right-hand side here must have something wrong with it, because this can't be a physics equation. Great. The units of the left side of any equation that you write must be the units of the right side. And you can test that in variable equations. You don't have to have actual number or numerical quantities like 1.5 meters. You can just look at this and say, oh, this doesn't work. The units don't work. Now let's do an example. Let's say there's a bullet that is in a gun and it experiences constant acceleration throughout the length of the barrel. And this is a pretty long gun barrel, 120 centimeters long, and it leaves at about 640 meters per second. I want you to tell me how much time it spent in the barrel. Okay, here are the problem-solving requirements for the constant A problem. You might want to draw, a cartoon. You must draw what is called a motion map. A motion map is an example of a qualitative representation. We're going to have lots of qualitative representations, and we're going to have a qualitative representation that we use for different types of problems in different units. For example, motion maps are our qualitative representation for constant acceleration. When we talk about force problems, we're going to have what's called free body diagrams. And so we're going to learn different qualitative representations. And the point of a qualitative representation is to strip away all of the information that you kind of don't need and distill down to the essence what's actually going on. And in particular, you're getting rid of the numbers and talking instead of how much there is in a quantitative sense. You're talking in a qualitative sense of, is the value 0 or positive or negative and getting bigger or getting smaller? What direction? So let me talk a little bit about this motion map. A motion map describes 2 time instants. In this case, the bullet in the barrel starts at rest. Do you see how that was tacit in the problem? Unsaid but implied. And then, at some later time, it's at a different location. and it has a velocity going out of the barrel. So here's what a motion map includes. A dot showing the initial position, a dot showing the later position of an object. See, we're not drawing a picture of a bullet, we're just saying this dot, because we don't really need the shape of the bullet to solve this problem. Velocity arrows on both of those dots, or if one of the velocities is 0, as it is in this case, we label equals 0 to show the velocity is really 0. We draw a direction, we draw an arrow for the direction of acceleration. We label the displacement with these angle brackets. By the way, if you have trouble making angle brackets, practice them and come and talk to me and I'll show you how to make them. Angle brackets. Learn how to make these. I had trouble with it at first, but now I can do it, and it's important that I can do it. Make sure you can draw good, I'm sorry, I shouldn't say angle brackets, curly brackets. So label the displacement. If it's a horizontal displacement, call it delta x. If it's a vertical displacement, we're actually going to call it delta y. Don't label any other quantities other than 0. Qualitative representation. It's sometimes nice to label the direction that you're choosing to call positive because it's an arbitrary choice and it will help the reader of your problem to understand what you're calling positive and negative. A motion map. See how this is just the most simple distillation of the bullet coming out of the gun? After your motion map, I'd like you to list your variables given and asked for. Convert them to base units, so meters, seconds, meters per second, kilograms, convert them here in your list of variables. So in this problem, it was given that the gun barrel, the distance, the displacement that the bullet traveled between the first and the second time instant was 120 centimeters, and there's my little conversion. That's 1.2 meters. That is the length of time between the bullet starting to be fired and the bullet coming out of the gun. The initial velocity of the bullet is 0. The final velocity when it exits the barrel is 640 meters per second. And the question is asking, how much time did the bullet spend in the barrel? What is delta t equal to? I told you these problems would give you 3 variables and ask a 4th. So the next thing that we have to do, given values converted to base units, list the desired variable. Don't include extraneous variables. You do not need, nor is the problem telling you anything about the acceleration in this problem. So don't say anything about the acceleration. Don't solve for the unknown acceleration and then use it to solve for delta t, because you don't need to. Don't include extraneous variables. Okay, let's pick the equation that links these 4 variables. That will help us find the unknown. This is it. Go back here, delta x equals blah, 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 blah. Great. That's the equation in general form. Don't rearrange the equation yet. Write it as it appears on this page, as your classmates have memorized it. Otherwise, you're trying to do 2 things at once. Recall it and manipulate it, and it's unreasonable to ask a brain to do that. General form. Write it in variables, unmodified from how we memorized it. If there is a 0 value, substitute that 0 right away with a little arrow to a 0. That makes the algebra much easier. Next, I want you to solve completely algebraically. That is to say, delta t equals, and then no numerical values on the right side. Just solve in terms of algebra from this equation. Check to see that the units work. Remember I said that that was useful? We're saying that delta t is 2 delta x over v2. Well, is it possible that a length divided by a velocity would be an amount of time? Let's see, meters divided by meters per second. Yes, indeed, that is equal to seconds, because the meters cancel, and then the seconds is in the denominator of a denominator, so it's in the numerator. Now, write out your substitution with units. This is your algebraic solution. Substitute the values from your values list with units. There's actually a point given on free responses in some AP questions for substitution with units. So you do have to do this. Then you get an answer. And you notice, you go to your calculator 1 time only. You have a complete algebraic solution. Then you plug in the numbers in 1 line on your calculator. Really it really cuts down the opportunity for calculator error. Obey all the writing conventions in our writing conventions document, including, look, I have a leading 0 there. That's an example of one of our writing conventions. I don't write 0.0083, so we don't write 0.0038, we write 0.0038. That's to avoid confusion. If a nurse were to be carrying out your doctor's orders and not see a decimal point, it would be a big bummer. This is another written out example of a constant acceleration problem. Notice that here, if I've defined this direction to the right as positive, the car's brakes provide a deceleration of 10 meters per second squared. Notice that the acceleration has a negative value because the acceleration is in the direction that I have called negative. Review this and make sure that you understand it. And you should have the skills that you need in order to do the constant acceleration homework problems.